Okay, this is a quick introduction to Chapter 4, Redox Reactions. We did this in Year 11. So redox stands for reduction, oxidation reactions. So it's two half reactions that between them contribute to making a redox reaction. We'll look at the classic metals reacting with non-metals, and then other occasions where metals can react with other metals or non-metals can react with other non-metals. Do half equations and balancing overall equations. So oxidation is the loss of electrons, and reduction is the gain of electrons. The oil rig, oxidation is the loss and reduction is the gain, is a way of remembering those. These ideas are fairly simplistic and only really work literally for ionic reactions. For covalent bonds, the electrons are shared and maybe equally, or if they lose and gain, then unequally. So the first example is the classic one between metals and non-metals. So all the metals over here losing electrons and giving them to the non-metals over here. So the reason that metals lose their valence electrons, it's valence electrons that we're talking about all the time, and non-metals gain them is because non-metals have a higher electronegativity. They are more attractive to electrons because they have a higher core charge. So they will take the valence electrons from metal atoms, and the metal atoms will lose their valence electron until the shell underneath is full, and then they won't lose any more. And the non-metal will gain electrons until their valence shell is full, and then they won't gain any more. So the metal atoms and the non-metal atoms become ions in that example. This is just another drawing, a diagram showing it, an example. So sodium has 1 electron in its outer shell, chlorine has 7, so the sodium loses 1 until it becomes 2, 8, and 8, and the 2 and 8, and the chlorine gains 1 until it becomes 2, 8, and 8. So we had the electronegativity values in your data booklet last year, and I'm not sure if the year 12's got electronegativity numbers. I don't think it has. But chlorine has a higher electronegativity than sodium, and if the difference between them is greater than 1.5, then it will lose and gain totally to become ions. This is another example of a metal, calcium, and the chlorine again. Calcium loses 2, each chlorine has to gain 1. So calcium becomes 2 plus, chlorine becomes 1 minus. Okay, so those two are broken up into half equations. One of the half equations where what's losing the electrons, and the other half what's gaining. When you do half equations, you must remember that the charge on both sides of the arrow must be equal, and the total number of atoms on each side of each element must be equal. Okay, so an example is our example that we've done before, sodium with chlorine. So in reality, you don't just have one sodium atom by itself, you have a whole lot of metal, and chlorine comes as molecules sharing. So if we broke it up, the sodium is what is actually losing electrons. Must remember to put the electron that's being lost on this side of the arrow. Oxidation is the loss. So you notice this is 1 plus, 1 minus, so those two cancel out to become no charge on this side and no charge on that side. You must write the negative on the electron. Reduction is the gain of electrons. Each chlorine needs 1 more, and there are 2 chlorine sharing at the moment, so they get 1 each, so that you become 2 chlorine ions. Overall equations, when you put these two half equations together, you must make sure that the number of electrons that is being lost by one equation is balanced by the amount being gained. So this first equation only loses, each sodium only loses 1 electron, so you have to do this reaction twice so that you get 2 electrons for the chlorine. When you put the two together, you put everything on the left together, just making sure that you've got 2 of these. So 2 sodium and then the chlorine and the electrons, and then everything on the right, all the products together, so 2 sodium and 2 electrons, and then the 2 chlorine. Then you tidy it up, get rid of whatever's the same on both sides, and then you can put this together and write it as a salt. So you've got sodium, 2 chlorine ions, 2 sodium ions. You can write it together as a solid salt. I've left the state off there. Okay, so that's the classic metals losing, non-metals gaining until they get a full outer shell. You can also have metals reacting with other metals because not all metals have the same electronegativity. The first group are very poor at holding their valence electrons. They lose them readily. They have a low electronegativity. These have a slightly higher electronegativity, and some of these others have a higher electronegativity. So electrons, if something's going to lose it, these would lose. So if we put a metal, so the copper atoms here have their outer shell electrons when it's in the metal form. They're just passing them around. This is copper ions that have lost their electrons. So oxidation reaction, if you have copper metal and silver ions together, silver is a more electronegative metal than copper, so it will take the electrons from the copper to become silver metal, and the copper will lose them. So you can have a reaction between two metals as long as one of them is in the metallic form, has its electrons, and the other is the ion. Same thing, you have to balance the overall charge when you put it together. Each silver only needs 1, so you need to do that twice when you write the overall, and then you cancel them out. As this would be a salt, it would be silver chloride or silver nitrate or silver oxide or something. The anion is a spectator ion. It's not involved in this reaction, so we can just leave it off. It makes it less complicated. So if it was silver chloride, you would make copper chloride, which would be floating around in solution, and you've got silver metal rather than copper metal. Alright, so that's reactions between a metal that has its electrons and a metal ion that's lost them. You can have reactions between non-metals too. So covalent molecules. Covalent atoms are both electronegative. They both attract electrons. So as they both attract electrons, non-metals are normally sharing electrons. So in this case we've got hydrogen sharing its electrons to become H2, and oxygen. Each oxygen has 6 electrons in its outer shell. It needs 2 more. It can share 2 from another oxygen to make a double bond. If you react hydrogen H2 with oxygen, then you'll form water. So the oxygen, instead of sharing its 2 electrons with another oxygen, which would be equally, each oxygen is as attractive to electrons as the other, and each hydrogen is as attractive to electrons as the other. When you put them together, the oxygen is more electronegative than the hydrogen, so the electrons are being shared with the oxygen but not shared equally. So if we did half equations for that, we start off with H2 sharing electrons. When you write it, this is artificial. It doesn't become hydrogen ions, and the oxygen molecule doesn't actually get the electrons to become oxygen ions, but you can write it to show this. We're just doing this as an example. So you've got 2 oxygen atoms sharing each electron, the electrons, and if they got extra ones, then you would have 2 oxygen ions. Each needs 2, because there's 2 of them, you'd need 4 electrons altogether. If you put them together, this reaction here needs to happen twice. So you would have 2H2 plus O2 plus 4 electrons, and I've already cancelled out the electrons here. And 4H plus 2 of these together. So this is artificial. Really, these 4 hydrogens and 2 oxygens become two water molecules.